and make a short introduction. So we are welcome everyone, and the topic of this week is going to be phase transitions in crystal systems. And as a high energy physicist, for example, I'm quite I usually get a bit scared when people talk about complicated crystal symmetries. So I requested that that we have some lectures to remind us or to teach us about this, and we are very happy that Sylvain Ravy has agreed to give us a tutorial and a reminder about crystallographic group symmetry. So Sylvain is an experimental, mostly physicist who works in particular at the synchrotron Soleil, where he uses synchrotron radiation in particular to study structure of all various interesting materials and so on. So he has this crystal symmetries on his fingertips, and so he's going to tell us how to think about these things. So please, Sylvain, we are very happy to have you.
Thank you. Can you hear me like that? It's okay?
Yes.
Okay. So this is this comes from a lecture I gave to a student in Master 2 in France. So I've tried to remove very basic things as I was required by your organizers, and I hope that this lecture will help you for the other lectures, in particular in this afternoon. So I know that you know what is symmetry. So it's, I'm sorry, I have to move. Okay, sorry. So symmetry is a property of invariance, of course, of an object. So the object in condensed matter physics can be a crystal, but other things also, a liquid crystal, for example, whatever. Invariance under a space transformation. So this transformation is, in a very general way, a bijection which maps something geometric set in itself, as it is indicated here. But we are more interested today in special transformation, which are the isometries. So isometries, as you know, are distance preserving maps. And in this lecture, I will try to show you that we need two types of isometry actually to understand a crystal, which are a little bit different. So the first one are affine isometry. They transform points, and they belong to so-called space groups. And they are used to describe the microscopic properties of crystals. For example, if you want to calculate the electronic structure, if you want to calculate the excitation, vibrations, you need these symmetries. So, of course, you have the translations, rotations, reflections, but you have also, we will see that, glide planes, more complex symmetries like screw axes and stuff like that. So that's the affine isometry. And the second sort of isometries are called linear isometries, and they transforms vectors or directions, and they belong to point groups, and they describe the macroscopic properties of crystals. For example, response functions. You apply an electric field to your system and you want to know what's happening in the system. You need to use this sort of isometry, which are actually more simple, like rotations or reflections or combinations. We will see that in a few minutes. So basically, we have, remember that we have two types of symmetries here in crystals. The symmetries concerning the points, the atoms, and the symmetries concerning the directions, the vectors. And I will start by these ones. So in the plane, you you have only two types of isometries, the direct ones and the indirect ones. So that's very simple. It's the rotation for the direct one. And you can see here the representation by a matrix that you know very well. And the indirect ones are refractions through an axis which has an angle theta over 2 here. And this is represented by this matrix here. So this is the case of 2D, and this is actually the groups which are called SO2 and O2 in general, right? So in 3D, it's a little bit more tricky. So you still have two types of isometries, the direct ones, which are again the rotations about an axis in 3D. So in this sketch here, you can see a vertical axis. This is a point, but you have to remember that we act on vectors, right? So this direction from here to here can be rotated by an angle theta around about this vertical axis here. And this is represented by this matrix here. And this is the only direct symmetries we have, isometries we have in 3D. For the indirect symmetries, it's a little bit more complicated. And the more general symmetries are called rotoreflections. So here you have the matrix first with the -1 here. And you have first a rotation by an angle theta, and then a reflection with respect to this plane. And this is called a mirror symmetry. So this general operation, symmetry operation, have well-known specific cases. So if you take, for example, theta, pi for theta, you have the simple inversion here. If you take theta equals 0, you have just refraction through this mirror. And there is another type of symmetry, which is called rotoinversion, but well, I don't insist on that, but whatever. This is all the isometries you can have in 3 dimensions. So now we will try to sort them, to regroup them in groups and to see what's happening. And to do that, there is a easy way to represent them that all people use. And this is the stereographic projection that you may know. So the purpose is to have a representation of a direction. So take, for example, the direction, OM here, and this is a unit sphere. So take the opposite pole to the M point and draw a line from S to M. It intersects the equator at point P, and this is the projection of the direction, okay? So this point, actually, P point, actually represents the projection of this direction, okay? So here, for example, you have the point P, and if your point M is in the southern hemisphere, you take the North Pole to get the P prime projection, okay? So everyone use this projection because actually it's a conformed transformation in preserved angles, but it's not affine, of course. Okay, some simple example of how to represent this symmetry. So here you have the equator of this our projection, and here it's an example of a twofold axis of rotation. So take this point, which is again a direction, and you rotate it by pi on this way, and this is how you represent simply the twofold axis. This twofold axis can be horizontal like this. In that case, this point here will change hemisphere, and we represent it by a small circle here. This is a 3-fold axis. This is a 4-fold axis, a 5-fold axis, etc. For mirrors, we use big lines here, like that. If the mirror is in the plane, it is like this. If the mirror is vertical, like that, and tilted like this. And then you have a lot of different symbols, but that, I think it's not important for you. I just show you this representation because it is always used in the point group. Maybe an important thing to consider is the combination of symmetries. So there is 2 simple rules you can remember. The first one is the combination of 2 mirror symmetries, 2 refractions, which have an angle alpha. And if you do this combination, it is equivalent to a rotation of angle by an angle 2 alpha. So the combination of 2 indirect symmetries gives you the direct symmetry, the rotation. Okay. And then also important rule, the composition of 2 rotation is another rotation. And this is called the Euler construction, where you have 2 rotation, for example, N1 fold rotation, N2 fold rotation, and you combine them to get N3 fold rotation. And these are related like that. This is important. You can see that you have a spherical triangle here with angle pi over N1, etc. So this is called Euler construction. So this is the main composition of symmetry that are useful for us today. Of course, the most important point is that the set of symmetries of an object forms a group G, which is called a point group. So it has all the characteristic of normal group. I don't explain you what it is. Maybe something which is important to keep in mind is that in general, groups in 3D are not commutative because rotation don't commute. As you know, there is a small example here of 2 rotation, one vertical, one horizontal, which gives different possibility at the end. A very simple example, just to show how it works. Take a table from the top. So here you have 4 legs. So here you have a 2-fold symmetry because it's a rectangle. And you have 2 mirror symmetry. For example, that one, MY. You go from this leg to that one, this leg to that one, okay? And you have 4 elements if you're in your group. The identity, of course, the 2-fold rotation, and the 2 related mirror symmetries. So this group is represented like that in the stereographic projection, the 2-fold with this sort of eye, black eye, and these lines for the mirrors. And here is the 4 transformation of a direction. Again, this is a direction. So with this mirror, it goes there, the second mirror there, the first mirror there, and you have a group of the multiplicity equal 4, which is the number of elements of the point group.
And what do those symbols 2mm stand for?
I will explain that. This
Okay.
special notation.
Okay, thanks.
Yes, so you have a very interesting constraint here if you want to obtain all the possible point groups. So if you look at this Euler construction again, and our 3 rotation axes that you can see here. So these 3 axes define a spherical triangle, as I mentioned previously, with angles pi over N1, pi over n2 and pi over n3. And as you know, the sum of the angles of a spherical triangle is larger than pi. We don't need to know exactly how much it is. It's just important to know that it's larger than pi. So this gives you a condition on the n1, n2, n3, which is that formula, 1 over n1, blah, 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 larger than 1. And actually, there is a very few number. Actually, I should not say that because it's infinite, but you have a very few type of a group which satisfy this simple inequation. So the first one is when n is whatever, and then you have only two to be larger than 1. And these are called dihedral groups. And this is because you have n-fold axis of symmetry, for example, vertical here, sorry, and 2n two-fold symmetry normal to this axis. So these are called dihedral groups. And then we have multi-axial groups, and we have only 3 possibilities: 2, 3, 3, 2, 3, 4, and 2, 3, 5. And I will show you what it represents. But first, maybe, okay, so that's the complete classification of the point group, and usually people find that a little bit scary. And this is a classification according to the main symmetry here. So you have the triclinic for just one symmetry, monoclinic for two-fold symmetry, orthorhombic when you have different two-fold symmetry crossing, trigonal when you have three-fold symmetry, tetragonal when you have four-fold symmetry, hexagonal when you have five-fold symmetry. And then you can have, I should not have, but I skipped five-fold symmetry, which is possible here. But you can also have seven-fold symmetry, eight-fold symmetry, blah, 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 and infinite symmetry, where you reach what is called the Curie's limiting groups with a continuous symmetry. So what you can see here also is that you have groups which are chiral, which means they don't have indirect symmetries. You have groups which are called improper, which are groups with indirect symmetry except centrosymmetry. And in orange, you have centrosymmetric groups. Okay, so this is the classification you can find on almost all the books of symmetry in condensed matter physics. And I can just enter into the details for the multi-axial groups, which are the most complicated, I would say. So here you have the representation. So again, this is a stereographic projection. For example, I don't know, a simple one is 2, 3. So here in the vertical direction, you have an axis, a two-fold axis. In the horizontal direction, you have another one. In this direction, another one. And you have 4 three-fold axes, which are at a definite angle, which is the angle of a cube, actually, but whatever. So here you can see some example taken from the well-known Platonic solid. So you know that we have only 5 regular polyhedron, convex polyhedron to be precise. So you have the tetrahedron, which group of symmetry is 4 bar 3m. 4 bar means an axe of 4, a fourfold rotation, and then an inversion. And you have the threefold symmetry from the center to the extremity here. And you have a mirror symmetry. Then you have cube and octahedron. which have this very well known M3 bar M symmetry with four-fold symmetry on the face of the cube, two-fold symmetry on the shape here, and three-fold symmetry on the summit. And then you have the five-fold symmetry polyhedron, which are called icosahedron and dodecahedron, which have the most complex symmetry of all these point groups, 5 bar, 3 bar, M, where you can see we have a five-fold symmetries, three-fold symmetry, and two-fold symmetries. Okay, so that are the multi-axial groups, and again, everything is indicated in this table. Sorry. Okay, this is the hydron, this is the decahedron, whatever. That's the notation. So notation is something very boring, to be honest, and not so easy. So we use numbers to describe the rotation, and we use the letter M to indicate the mirror symmetry. And when M divides somehow the axis, it means that the mirror is normal to the axis of symmetry. Okay, so here I chose an example where you have a vertical four-fold symmetry. That's a dihedral group, and then you have two-fold axis normal to this direction. And you have mirror symmetry also almost everywhere. So you have a mirror symmetry normal to the four-fold axis, etc., etc. So it's difficult to explain in detail all these notations. They are called Hermann-Mauguin. They are used in condensed matter physics, but people who are chemists or spectroscopists prefer the so-called Schoenflies notations, which look like this: Cn, Dn, D is for dihedral, C for cyclic, etc. So that group, for example, which is, so that's in French, sorry, I forget to translate, whatever, a reduced notation, 4 over M, 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 this is D for H in the Schoenflies notation. So all the elements of symmetry indicated here are generators of the point group, actually. So knowing this, you are able to reconstruct to retrieve all the symmetries of your group, but unfortunately, but for consistency, they are not the minimum generator. So you could need less than all these to retrieve all the symmetries. Okay. And then you have interesting limiting point groups that I described previously. They are called Curie's group, but I think it's maybe only in France that we call them this way, because you know that Pierre Curie was French, and I think he first discovered this group. And these groups are usually associated to special geometric figures. For example, here the rotating cone is in the group infinity. The twisted cylinder is in the group infinity 2, which means that you have an infinite axis of rotation, vertical, and the all-around axis of symmetry 2, etc., etc., the cone, the cylinder, the rotating sphere, the sphere. And these can be associated to physical quantities. For example, let's take the simplest one, which is the polar vector, like an electric field or a force. This is actually the group O2. So this belongs to the group of the cone, which is infinity M, which means that you have an infinity axis vertical and all the M vector containing this axis. And this is the symmetry of a polar vector. So this is different from an axial vector like the magnetic field, which has the symmetry of the rotating cylinder. So you have also an infinite axis, vertical, but the mirror is, there is only one mirror, which is normal to this axis. And you can play the same game with other quantities. For example, a polar tensor belongs to the group of the cylinder. An axial scalar, like chirality, for example, is belongs to this infinity group. And a polar scalar, like a pressure or mass, belongs to the group of a sphere. Okay, so I think that's it. What I wanted to explain about the point group. And except if you have a question, I can skip to I can go to the second. So sorry, I think I have to stop that. And
yeah, can I ask this? There is an associated, for example, the occupied volume of this corresponding to this different group symmetry. Like if I have to locate a number of atoms, if there is like a symmetry that minimizes the occupied volume, for example.
The symmetry, I don't understand your question. Symmetry which minimize what?
That minimize, for example, the occupied volume. I mean, I don't know, like given a number of atoms, how is the arrangement that minimize the occupied volume? Or, by the way, it is a well-posed question. I don't know.
Point symmetry.
The packing problem, yeah.
For point symmetry.
Okay, so you have spheres, for example, and you want to find the arrangement with the less volume. That's the question.
Yes.
But I think that's a question which is not completely related to symmetry, right? But my feeling is that the icosahedron is the solution, but I'm not completely sure now.
Okay.
Is that your question, or?
Yes, I mean, I had in mind, like, for example, the packing of sphere.
Yeah, for small, I think for small, yeah.
Symmetry. So I was thinking that maybe there are when the symmetry that allows like to minimize volume, for example.
Yeah.
Something like that.
I think the answer is that for a small number of atoms, the solution is the dodecahedron here. If you put the spheres here, no, sorry, the icosahedron here. I'm sorry. And then you have the larger number of symmetry, which minimize the volume, I guess. But this is for a small number of atoms. For a crystal, fivefold symmetry is forbidden, as we will see. So that's a bit different.
Okay, thanks.
Okay, so let's switch to that one. Okay, so we have seen the point groups, so the symmetries which transform direction, and now we will switch to the other type of symmetries which transform positions. And so, of course, we will deal with the most obvious symmetry, which is the translation symmetry for crystals. So, as you know, crystals are described by lattices, and these lattices are described by unit cells, and unit cells is a polyhedra with three vectors, three lattice parameters, A, B, C, and three angles, which a priori could be anything. And These are now convention. We have 4 types of unit cells. The primitive one with only 1 node in your cell. The face-centered, where you have 4 nodes in the cell. The body-centered, where you have 2 in your cell. And the base-centered, when you center only 2 faces, opposite faces here. So this is, of course, conventional, but this is how we describe the lattices, right? Yes, so this is
Can I ask
very...
a question about this, naive
yeah.
question? So, but for example, what happens if I take face-centered unit cell and an atom in the middle? Like trying to combine face-centered and body-centered, then why is this not in the list?
So actually at each nodes, you will associate a motif consisting of a group of atoms. So the atoms, the same group of atoms, which will be around each node here. Okay.
Okay. So each node represents more than 1 atom. Okay.
Yeah.
Okay. Thanks.
Yes. Then this is a very important property that you know, of course, is that for a periodic lattice, a very few symmetries are possible. So this is not very complicated to demonstrate. I can do it very quickly here. If you take a center of rotation here and there, related by a translation of the lattice, you apply this rotation once here to get the point B. You apply the rotation A prime to get the point B prime. And then you get the vector B prime, which should be a multiple of the translation right T. And you can calculate easily the length of this B prime, which is given by that formula. And this gives you nice constraints on what is possible. And you wind up with only 5 possibilities. So the only symmetries compatible with translation are symmetries 2-fold, 3-fold, 4-fold, 6-fold, of course, no symmetry, element symmetry, unit symmetry, sorry. And you don't have the 5-fold symmetry, and you don't have more than 7-fold symmetry. It is just impossible, incompatible with periodicity. So this, of course, can be represented by this small graph. Here you have, imagine that you want to have tilings of your kitchen with tiles, rectangular tiles, so symmetry 2, so you can do that easily. With tiles of symmetry 4, you can do that also easily. With tiles of symmetry 3, no problem. Symmetry 6, no problem. But you can see that you cannot do that with pentagons because you have gaps. And you can do that, you cannot do that with octagons or larger because you have overlaps. So the only way to have a tiling of the plane is to use symmetry 2, 3, 4, or 6, or 1, period. That's not, there is no other possibilities. So this is actually the great astronomer Kepler who not discovered maybe, but tried to get a little bit further in this problem. And as you know, probably, yeah.
So a question.
Yeah.
So if you allow 2 different kinds of tiles, could you classify as well?
That's yes. If you allow 2 different, that's another story. So here we have only 1 tile, and we use periodicity. If you allow for 2 tiles, this is another world, really. So let me come back. I will answer your question, but let me come back to Kepler. Kepler this is a nice drawing by Kepler. So you can see that he well understood that 5-fold symmetry was not possible. And this 7-fold symmetry was not possible either. And he actually tried to do 5-fold symmetry tillings. And these are old drawings of Kepler, which are quite nice. And he was very close to discover what we know now as a Penrose tilling. So Penrose tilling are 5-fold symmetry tillings, but they are not periodic, and they are formed by 2 types of tiles that are not so easy to see here, but you have a big lozenge and a thin lozenge here, 2 types of tiles. And so you can construct, you can till your plane with a 5-fold symmetry, but you use 2 types of tiles. So this may answer your question. Can you tile the plane with 2 tiles? Yes. And we can obtain forbidden symmetries this way, for example, with this Penrose tilling. But we can also do that for symmetry 7, 8, 9, whatever. It's always possible with different tiles to have the tilling you want, but it's not periodic. Periodicity implies that you have 2, 3, 4, or 6-fold symmetries. Okay. So then you can try to find the possible 2D and 3D lattices. So in 2D, we have only 5 possible lattices, so-called oblique, rectangular, 2 type, centered, not centered, a square, and an hexagonal. And then if you want to construct all the lattices in 3D, you have to pile up all these 2D, and there is different way to do that. And if you do that properly, you obtain these famous Bravey lattices. So there is a 14 lattice modes, which are classified in 7 systems according to their symmetry. So here, for example, you have the triclinic. So you have no angles. All angles are different and different from 90 degrees. Etymology here means clinic means tilted in Greek. So triclinic means 3 times tilted. So which means that you are tilted in the 3 directions. Right? Monoclinic it's 1 time tilted. You have just 1 angle different of 90 degrees with 2 modes, centered, base centered, and that. And blah, blah, blah. You have orthorhombic for when you have different 2-fold axes, tetragonal when you have 4-fold axes, rhomboedric when you have 3-fold axes, hexagonal when you have 6-fold axes, and cubic, this is the multi-axis lattice, where you have again the 4-fold axis here, vertical, 3-fold axis in the large diagonal, and 2-fold axis in the small diagonal.
But
so these are
can I ask a question?
Yeah, so sure.
Just from the formal point of view, what exactly are we classifying here? Because, for example, the 2 monoclinic lattices, they have the same symmetry to M. So why are they different? What is the mathematical property that that is different? I mean, I understand that picture looks different, but mathematically, what is it that is different?
Good question. Yes, good question. I don't know how to answer mathematically. They represent 2 different lattices for sure, and
they
have the same symmetry. They have exactly the same symmetry. Well, I don't know. I have to think.
Does this have to do with different representations?
Sorry?
Does this have to do with different representations of the same group?
Yeah, maybe. Yeah, maybe. I don't know. I have to think. Of course, the lattices are different, as you said, but mathematically, I don't know. I will think during the presentation. Maybe I will have the solution at the end.
No, but for example, then I can ask, okay, why can't I consider more lattices where I add also points, for example, on the top of this and on the bottom? Then I can produce even more different looking pictures.
No. You can show that whatever you do, this corresponds to one of these lattices.
Because I will,
Even if you think that, for example, you could say, okay, let's take this tetragonal and do it face-centered. But actually, if you face-centered tetragonal is equivalent, it is equivalent to a centered tetragonal.
Because I will be able to shift
exactly. You can
lattice.
change you can change the unit cell and come back to this solution. Yeah.
Okay. Thanks.
So the and this solution are here. Yeah.
Okay.
That okay?
Thank you.
Okay, Brave lattices. Then, so then we can come back to the what is called crystal classes, which are the point group which are compatible with periodicity. So if you have a crystal, a periodic crystal, you can ask what is his point group, and he's one of these 32. Okay. So he looks very much like the table I showed you 30 minutes ago. But I have removed, of course, all the 5-fold symmetry and all the symmetries larger than 7. And that's a strong limitation. And so we have only 32 crystal classes. And they are classified according to the same crystal systems as we see. Okay. So we have again triclinic, monoclinic, blah, 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 and cubic. So that's the only possibilities. And we can retrieve the same properties here, chiral group, centrosymmetric groups, improper groups, and whatever. Okay. That's, I think, a very important slide related to what you want to do. There is a relation group subgroup between all these 7 systems. And these are indicated by these arrows. And this is important because I have 2 examples here to show that. You can go from cubic to tetragonal, for example, in a continuous way. But because, for example, tetragonal and trigonal have no relation group subgroup, you cannot go continuously from a tetragonal system to a trigonal system. So, for example, here you have a tetragonal crystal with a unit cell like that, whatever, you have atoms in it, we don't care. And then you just increase a little bit the size, continuously the size of this part, and you are losing one symmetry, and then you are in the orthorhombic group, and you can do that continuously. You have the same example here, I mean the same continuous stuff. Here you have 2 stars, two triangles, which form a star of 6-fold symmetry, and then you shrink one triangle continuously again, and you go from hexagonal symmetry to trigonal symmetry in a continuous way. And this continuous way, of course, is related to second-order phase transformation. And when you don't have this relation, for example, again, from, I don't know, hexagonal to tetragonal, there is no relation. So you cannot have second-order continuous phase transition from an hexagonal symmetry to a tetragonal symmetry. You have only first-order phase transition, if you have, if any. Okay, so that's a very important concept, of course. Here I have some funny example just to show you that these symmetries are a little bit more tricky than the point groups. So here you have a drawing of Moritz Escher, who is a Dutch graphic artist. And he actually draw a lot of tessellation, nice tessellation like that one. So here you have seashells. So you can recognize here a sea star. This I don't know in English, maybe scallop, something like that. And this is a green sea snail and a black sea snail. And the question is, where are the symmetries here? So actually, that's not so easy to find. I regret not to be with you because we could have played, but that's virtual. But the solution is that one. And you have a fourfold symmetry here. So you go from this snail to that one, to that one, to that one, for example. But surprisingly, here you don't have a fourfold symmetry. And this is not easy to see. It's because if you see this black snail here, if you rotate around this point by 90 degrees, you don't get that one, okay? Because it's not oriented the same way. So you don't have a fourfold symmetry here, but only a twofold symmetry, okay? And this is a group which is called P4, which is a chiral group. So we have no inversion, no mirror symmetry, and this is chiral. If it is chiral, it means that we have two types of crystals. Let me call that the left crystal. And if you take a mirror symmetry, you will get a right crystal, which are different because the group is chiral. Okay, so that's the first example. We have not a lot of symmetries, and we don't have the new symmetries I will show you now. Again, with Escher example. So this is a tessellation called angels and demons. So you can see the angel in white and the demons in black. And here we have a lot of symmetries. That's actually very complicated. It does not sound like, but it is. So first one, we have the fourfold symmetries, which are here. Then we have twofold symmetries, which are here. So for example, at that point, you take the angel and rotate around by 180 degrees and you get that one, okay? Then we have mirror symmetries like the blue ones here. So if you take, for example, this line, take this wing, it goes this way, okay? So we have the symmetry. Because of the fourfold symmetry, we have the same in the vertical direction. And then we have much more tricky symmetry, which are called glide planes. Glide planes are combination of translation and refraction. So this, of course, does not exist for point groups because we act only on directions, but here because we transform points which could have these symmetries. For example, this is not easy to show because I'm not with you, but take, for example, this glide plane here, okay, and take this angel, reverse angel here. So you first do a reflection. So it would have been here, but it's not. And you have to translate of half a translation to get it here, okay? So you first reflect and then you glide somehow. And this is a new symmetry, which is called a glide planes. So these symmetries are very important actually for crystals. There is a lot of such symmetries. And
is there some convention that you glide somewhere in the direction along the plane, like you showed us, or are you supposed to glide in the direction orthogonal to the plane?
No, you glide in the same direction as the plane. Yeah, yeah. There is a convention. Okay. Of course, you could glide anyway, but the convention is to glide that way. Yeah. Mm-hmm. And you have another type of symmetry. Okay, so sorry, there is another type of glide plane. So you see that it's this tessellation is quite complicated. You have rotation, different type of rotation, different type of reflection, glide planes, two type of glide planes. So that's not easy to find all. This is the name of the group, whatever. Sorry for the E, that's French. And so we have two new symmetries in 3D due to combination of translation and rotation or reflection. So the first one is what we just saw, the glide plane. So it's a combination of mirror symmetry and a periodicity. So half a periodicity, actually. For example, start from this point, you do the mirror, and you translate of T over 2, and then you do the same, and you translate T over 2, and you get the translation here. Okay. And then you have the same sort of symmetry, which are called screw axes with the rotation. So you can rotate, for example, this point, you rotate by the two-fold symmetry, and then you translate of half the periodicity. And you do that again, you rotate and translate. And you can do that for the two-fold symmetry, three-fold, four-fold, six-fold symmetry. And these are called screw axes. And there are new symmetries that we had not in the point group. So if now we want to find all the space group, this is much, much, much more complicated than for the point group. This has been done, I think, at the end of the 18th century by 3 people. And they did a lot of mistakes first, and then they found that there is actually 250 space groups that you can arrange in the 7 crystalline systems that we saw. And there is also a complex notation that I cannot explain in detail. That's only convention, but basically, for a space group, you first indicate the type of lattice you have. So this is a sampled lattice, okay? With it comes from German. It's inert-centered here, the I. Then you have screw axes for 1. You have a glide plane here. You have a mirror here, and you have another glide plane, which is D like diamond, whatever. What I think it's important to understand is that if you have a crystal whose microscopic symmetry are described by this group, we can ask the question, what is his point group to describe the macroscopic properties, okay? And the answer is that you take this notation and you remove everything concerning translation. So you remove the I because it's related to the lattice. You remove the screw axis and replace it by the simple axis. And you transform the glide plane in simple plane. And this is the point group of your system. So if you have a compound, a crystal, which have this space group, so if you want to calculate, I don't know, electronic structure, as I mentioned, you have to use all of these symmetries. But if you want to understand the microscopic symmetry, how it behave when you add a magnetic field like did in this direction or electric field in that direction, if you press in this direction, you have to use this point group, okay? So that's the 2 information you get from these. And okay, if you have everything, this is maybe a little bit too detailed, but whatever. Just to explain what is an asymmetric unit. An asymmetric unit is the smallest part of the tessellation you must have to reconstruct the whole crystal with the symmetry. And in that case, it is that one. So take this small triangle. It is asymmetric. There is no symmetry. So you can apply the mirror first, then the rotation, and then the translation, and then you obtain the whole tessellation. This is the summary, actually. So you have the linear symmetry, which give the point groups. You have 2 types of symmetry, rotation, rotoreflections. And if you consider the symmetry of position, not all the symmetries are allowed. You don't have 5-fold, for example. You have only those. You have 4-fold Bravais lattice, 32 crystal classes, and 250 space groups, and classified into 7 systems. That's a summary of all what I explained. And then I just want to to give you an example of phase transition, because you will have a lecture on that. Very simple concept. If you have two phase 1 and phase 2, with a space group G1 and space group G2. So Landau theory says that if there is no relation group subgroup, you have a first order transformation, first order transition. And if you have a group subgroup relation, you can define another parameter which characterizes the low temperature phase, which can be continuous, and then you have a second order transition, or discontinuous, and then you have a first order transition. And the classical example is barium titanate, which is a ferroelectric compound. And here you can see the polarization, which is actually the order parameter of this transition as a function of temperature. And you can see that, so this is explained here with the groups, but you can see that the polarization is in the 4-fold direction here, in the 3-fold direction here, and the 2-fold direction here, and 3-fold direction here. And because there is no relation group subgroup between orthorhombic or rhombohedral, you have first order phase transition here and there, same. And here, actually, the first one, you could have a second order phase transition, but because you have a coupling with the elasticity of the system, it's slightly first order here. So you can see that it's almost continuous. You have a small jump, which is actually very small. And I think that's it. I hope that this will help you a little bit.
Thanks very much, Sylvain. Yeah, this feels definitely going to be helpful. Are there any questions? I have a naive question about this point group and space group. So
yeah,
you said that if we know space group, then of course we can determine the point group.
Yeah.
But the point group is a group of rotations around a point, right?
Yes.
So if I have a crystal, it's just a periodic lattice and so on. So which point, like if I just look at some random point in the crystal and start rotating around it, it's not going to have any symmetry. I should choose the point carefully, so that when I rotate, so how do I choose this point? Of course.
So if you have a crystal, so you have some atoms.
Yeah.
And around these atoms, say you have some symmetries, for example, this screw axis or whatever.
Yeah. But point group refers to rotations around which of the atoms? Because there are many atoms.
No, because point groups refers to direction.
Yeah.
Not point.
But in practice, couldn't I just find this point group by looking at a particular atom and rotating around that atom and seeing if my
because for example, in that case, you have a 4-1 symmetry, which is a screw axis, but you don't have a 4-fold symmetry at the microscopic level. See, you have a 4-fold symmetry only for directions from a macroscopic point of view. That's the tricky thing.
So how do I determine in practice if I just stare at the crystal? I should say, this is the direction, and that direction looks. So I have to kind of average over the direction to see whether the two directions are equivalent. Is this the point?
Yes, of course. If you have a crystal, you can see how it responds to an electric field, and you can rotate, and you will discover all the symmetries. 4-fold, for example.
Mm-hmm.
But this not gives you the symmetry, the microscopic symmetry. The microscopic symmetry could be a screw axis and not a 4-fold.
Okay, I see.
So that's the subtlety.
Maybe this is Martin Zirnbauer speaking. Maybe I can make a quick comment. There's some language so I'm not an expert. Very far from knowing all these things that Sylvain just explained, but I know there is a language of symmetric group and non-symmetric group.
Yeah.
And I learned that the difference is the following. You can write an exact sequence where you, as always, you start with 0, the exact homomorphism of groups. You start with 0, then you put the translations, then comes the space group, and then comes the point group, and then you go back to 0 as you do in an exact sequence. And now the point is that this may either split or it may not split. So if you have some training in this kind of algebra, you understand the difference. And if it doesn't split, you call it non-symmetric. In that case, you get the point group as a quotient of the space group by the translations. But that mapping may not be canonical, yeah? Because the sequence doesn't split. So I don't know, but maybe this is just confusing. Yeah. But if you have some familiarity with these algebraic constructions, maybe it is helpful. So I'll shut up, that's all.
Yes, you're right to mention this concept of symmetric and non-symmetric, because it's actually my understanding of that is if your space group is symmetric, then the point group associated is a subgroup of it. Okay. So it means that if you have the macroscopic symmetries of the crystal, they are the same as the microscopic ones, okay, because they are subgroups. But if it is non-symmetric, it's more tricky because you can have these nasty screw axis or glide planes. And in that case, you have not the relation group subgroup between the space group and the point groups. Yeah. Is it clear?
Yeah, it's clear. It's clear. It's clear.
May I say something? Isn't it that for symmetric groups, you don't have glide planes or things like that, while with a non-symmetric group, you necessarily have some glide planes.
Yeah.
Or screw axis. Basically, that's it.
Yeah. Yes.
I also have another kind of practical question. So suppose that what is the basic, like the standard literature that everyone, because there are so many books using this thing, and the problem is that for a newcomer it's not clear, like probably some of these books are standard and others are less standard. So what is the standard, like, authoritative source on all this? Like, okay, there's some website that one should just use and forget about everything else. Yeah,
I don't know right now, but I can email you some standards books. Yes,
exactly. So because then it would be nice to say, okay, use this and just don't bother about everything else because it's either equivalent or
I will.
Yeah, okay, yes, that would be useful.
I will send you something.
Yeah, and also I imagine that all this is catalogized, and if I have some material, I have to look up with Symmetry. There's probably some website that should just look
there
it
are
up.
Tables. There are tables.
Okay,
with all symmetries.
Okay.
But still, I think almost every year people discover some mistakes in these tables because this is very complicated, and so sometimes people find, you forgot a glide plane somewhere. Yeah. Okay.
Okay. Yeah.
Guys.
Any other questions or comments?
Yes, I had a question. So in 2 dimensions, there is something called Archimedean lattices. There are 11 of those, I think. So it's lattices that look locally the same around each point or each vertex. So you have the same succession of polygons when you turn around any vertex. And so I was wondering, on one hand, does it have anything to do with this kind of classification? Can I get these 11 out of this?
So you call that Archimedean lattices?
Yes.
I'm sorry, I don't know. Maybe I know, but I don't. Let me just check quickly. Ah, okay, I see. Those are quite different, I guess. Yeah. Yes. I will check. I can answer if you want by email if I find something interesting.
Actually, I was wondering if something similar could be done in 3 dimensions.
In 3 dimensions, yeah, I see the
somehow when I go around a vertex, that I see
yeah.
the same polytopes when I look in a circle at a sphere around any vertex.
Okay, I don't know that. I can
or by Slack.
Sorry?
Put all this answer in Slack, in the Slack group.
Okay.
And so we can see all the.
Yeah, sure.
We can share with that.
Well, if it's too complicated, Sylvain, then you just email and then we post it.
We do it. Sure.
Up to you. We don't want to impose too much on your time. Okay, so it was very useful. Thanks a lot again, and
you're welcome.
Yeah. Bye, everyone.
Yeah.